Segment 14, Refraction and Reflection. Refraction is the bending of light as it moves from one medium into another. We've seen this many times if we've looked into a pond or another clear body of water, and we see how straight lines bend as they enter the water. So if you're looking, for example, at a post in the water at an angle, you'll see the post appear to have a bend in it as it breaks the surface of the water. This is a result of the change of the speed of light in different media, the speed of light in water being slower than the speed of light in air. And it's analogous to the situation you had if you had a marching band marching along a street and it got into a patch of rough ground where people had to walk more slowly, but the line was getting to that patch at an angle. The first person in would slow down first, the others would start to catch up, and that would turn the line as it went into the new medium. Well, how does this gather light? Well, it turns out if you shape the intersection between the two media, between the less dense and the more dense medium, between the medium with the higher speed of light and the lower speed of light, you can actually direct the rays in the direction you want them to go. And this is how refraction helps you to form images. Reflection is the property of sending light back in the direction that it's come from, or at least back in a similar direction. And this property can be used also to shape where the light is going. And a famous classical example is Archimedes and his troops at Syracuse burning the invading ships by polishing their shields until they shone, and they were flat shields, and then turning them so that all the reflections were concentrated at one point on one ship at a time, and setting the pitch on the decks on fire so that the ships burned and sank. So let's start with reflection. The rule for reflection is that if you have a plane mirror, a very flat mirror, and you define a line that forms a right angle with the surface of this mirror, this is called the normal to the surface, that an incident ray, that is parallel light coming in at a certain angle with respect to this normal, will be reflected at the same angle with respect to this normal. This is the angle of incidence equals the angle of reflection rule. When you have this kind of behavior, you can see how you might gather parallel light together. Objects like stars that are very, very far away, the light from them comes in essentially parallel. All the rays are parallel. The source is a point source, but it's instead of seeing spherical waves going out from that, the segment of the sphere you're seeing, because it's so far away, is essentially flat, and you have parallel light. And this means if you take a surface and you curve it in a concave way so that places farther away from the optical axis, the line through the center of the mirror that's parallel to the direction in which the light is traveling, if those parts that are farther from this optical axis are more curved, they bend the light in more, and if they're closer to the optical axis, they're less curved, they bend the light in less. And if you do this with just the right shape, you can bring the light to a common focus. The shape that does this most effectively is a parabolic shape, but a spherical shape does a pretty good job of the same thing. With refraction, you also need to shape the surfaces, and here what you're doing is trying to shape the surface so the light is bent as it enters the glass in the lens by an amount that's proportional to its distance from the axis. Again, so the farther from the axis, the more bent, and that's why the glass curves around, and you get that curvy shape that lenses have. And that then also brings the light to a common focus. And you'll notice in this illustration that the curvier the lens, the shorter the focal length, the more quickly the light is brought together. This becomes important because there's a limit to how curvy a lens you can make. It gets thicker and thicker, and it's harder to make it as accurately. How does this form an image? We've looked at what happens with point sources, but let's just ask ourselves what happens also with extended objects, with objects, say, like a candle. in this illustration, we see an example of what happens. Each point on the object is sending out rays in all directions, and a certain number of those rays are being gathered together by the lens. So if you imagine again an object that's right on the optical axis, and here it's the bottom of the candle that's on the optical axis, it's sending out rays in different directions that are hitting the lens. The lens focuses them and brings them back together again on the optical axis. But an object like the flame of the candle, which is off the optical axis at an angle, the light is hitting the lens at an angle, and so it forms to an image. It all comes together at a different place. Here, since it's above, it comes together below, and you wind up with each point on the candle coming into focus at a different point behind the lens. So the object is focused to an image, which is a map essentially of the brightness of the object on the other side of the lens by this property of refraction. With a mirror, it works very similarly, except instead of forming behind the mirror, it forms in front of the mirror. And again, the bottom of the candle again reimages to a point on the optical axis, where the top, the light is coming downward, and it continues downward as it's reflected, because the angle of incidence is a little higher, the angle of reflection is a little higher, so the image forms a little farther down, and all those points from the flame come back together again at a point that's the image of the flame.